Good morning or good afternoon, everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London in the UK, and this is the new episode of the Turbulence at the exascale podcast. As you may be aware, the aim of the podcast is to gather the view of the community regarding exascale computing for turbulent flow and what are the challenges and opportunity associated with exascale computing. So you may be aware the UK has launched the ExCALIBUR initiative, which is led by the Met Office, the UK Atomic Energy Authority, and the UK Research Innovation. And the aim of this initiative is to deliver research and innovative algorithm development to harness the power of exascale computing. And I led a working group on turbulence, part of this ExCALIBUR project. And this podcast for us is a great opportunity to better understand how we can better use pre-exascale and exascale computing to advance our knowledge of turbulent flows. So today my guest is Professor Dirk Pleiter. He's a professor of theoretical physics at Regensburg University in Germany, but more importantly for us, he's working at the Institute of Advanced Simulation at the Jülich Supercomputing Centre. For those who don't know where Jülich is, it's in Germany, of course, and I think if you draw a line between Aachen and Cologne, more or less in the middle, you have Jülich. So good afternoon, Dirk.
Hello, Sylvain.
It's a great pleasure to have you, and we are really looking to be seeing what's going on in Germany in terms of high performance computing. So I'm going to start my question. And for those who don't know you, please, can you tell us more about yourself, where you are from and what you have studied and where and how did you end up at the Jülich Supercomputing Centre?
Yeah, so by education, I'm a theoretical physicist. More specifically, I did my PhD in theoretical particle physics, doing simulations of the theory of strong interactions, that is the quantum chromodynamics. And that is a field which still continues to be, in terms of progress, very much limited in terms of the available compute power. So that's why this community has already, say, quite a long tradition of actually working on its own computers. Today's it's more, say, one optimizes basically the kind of configurations for this specific purpose, but in the past it was also about building computers which were specialized for lattice QCD simulations. And in the UK, also the UK QCD collaboration was very much involved in similar kind of activities and hosted, for instance, also systems like QCD-OC or then later also BlueGene-Q, which was also developed together with people coming from this field. I later moved then from a high energy physics lab to the Jülich Supercomputing Centre, which was for me also an opportunity to really move then in the field of computer science, more specifically computer architectures, and to also not only focus on the more narrow application area of lattice QCD, but to also be available for, say, a broad range of applications.
So what exactly is your role within the Institute for Advanced Simulation? What do you do on a daily basis?
Yeah. I'm leading there a research team on application-oriented technology development. And what is the purpose is to really, say, work in this border regime between, say, computer science and computational science. So to create understanding of what are, say, the requirements with respect to computer architectures when you look at the computational problems you want to try to solve, as well as also to try to create understanding of where do computer architectures move to, because say we have a lot of constraints in technologies, so that we take it into account when we think about, say, future infrastructures, IT infrastructures, but also more specifically of HPC architectures.
And now, just out of curiosity, how did you develop an interest in high performance computing and in computer science?
Well, initially it was a bit of a need for, say, the own research, and I was a bit in this not that usual situation of having been involved in developing computers, building these computers, operating these computers, and be at the same time also a user of myself on these computers, because I was running, say, lattice QCD simulations on these computers. And so it was, say, driven by, say, enabling science, but it was, of course, also the interest in computer architectures and the possibilities of these computer architectures, which still, say, also is my interest, but still what continues to be basically a driving factor for me is, the design of computers, the design of IT infrastructures is not a purpose of itself. It has to serve as a means for enabling science, and that is at the end, say, always say the best indication of whether something had been successful. What are the kind of science papers which could be produced with the kind of computers which we have put in place?
Oh, thank you. And what's the best thing about your current position with Jülich? Is it do you have the flexibility to investigate what you want, or do you have some constraint, or how this is working for you?
Well, what I appreciate very much about the Jülich Supercomputing Centre is that it's not just a data center which defines itself by operating a big system. Obviously, it plays an important role for the reputation of the center, but at the end, it is primarily a research institute. And it's this very tight integration of, say, developing, operating an infrastructure for research, as well as doing research within the same organization. And doing that for, say, a pretty broad range of applications. So we, of course, on our system, say, there's still a lot of people from lattice QCD which are running on these systems, and they have, of course, been, say, also one of the prime users of our new systems. I'm sure we will get back to that soon. But we have also, say, applications for material sciences. We have people working on Earth system modeling, and we have also, that is a more of a new area, say, a number of institutes for neuroscience and medicine. And we are one of the leading institutions in the Human Brain Project. So it's through this organization which also gave me, say, the opportunities to look into completely new areas of science and to work with completely new people and try to understand what kind of needs are there and how do we have to, say, develop IT infrastructures and computer architectures to meet these needs.
Fantastic. Can you tell us, for the people who are going to listen to this podcast and who are not familiar with the Jülich Supercomputer Centre, what type of supercomputers are on offer, and what are the recent new additions to the centre?
Yeah. So in the Jülich Supercomputing Centre is, in some sense, maybe a bit special in the sense of that we do not aim of having, say, one single very big system which would allow us to get to, say, as far as possible in the front of the top 500 list, but to rather have a certain level of diversity in order to be able to serve a broader application basis. In the past, that meant that we try to operate two large systems, one being, say, more a cluster style of system, which was suitable for, say, a broad range of applications where it was not necessarily expected that these applications scale to the full system, but only used also, say, a smaller fraction of the system, and had then in parallel another system which was an extremely scalable system, and that allows them to serve smaller application bases, but an application basis which was really in need of having, say, maximal compute performance. And that was, say, largely realized with multiple generations of BlueGene. Now, recently, we started to do a next step in the sense of not just having, say, these as being two different systems, but in trying to integrate them more and more. a first step to that in this direction was to have a consolidated storage infrastructure, so that if people were running a workflow where part of the workflow was running on one system, produce some data, it could write it into a storage system, which was also accessible from the other system. And now 2 years ago, one first step was done, and which is currently now coined under the term of modular supercomputing, is to say, okay, I mean, instead of having, say, a more slow storage system in between, why not directly couple two different kind of systems, so that you can really have then coupled workflows which can communicate in a very fast manner over high speed network, using then between the different MPI processes. And we have now two of these kind of systems. There's now an older such system where you have a cluster and a so-called booster, which is based on Intel's Knights Landing. And now during the last year, so during 2020, we realized a second of such system where we also have on the one hand a cluster. It's called the Jewels cluster. It's based on Intel Skylake processors. And it was now last year augmented with the Jewels booster, which is an almost 1,000 node system based on GPUs. So in this sense, it provides, say, more than an order of magnitude more of compute performance. Obviously, not all applications can leverage, say, GPUs, but we have seen that there is meanwhile already now quite a broad variety of applications which can leverage GPUs quite well, and we are now also pushing the application developers in really making best use of this full performance and to scale out then to this full booster system. And if people are, say, even, say, more challenging, and we see, say, needs for that in particular, for instance, in the area of system modeling, where we have, say, workflows where, say, the needs and the different components of the workflows are quite different, to realize then workflows where part of it is running on a cluster, so just on Intel Xeon processors, and another part is running then on the booster, so where you have then the acceleration by the GPUs.
That was fantastic. Just out of curiosity, if I am a German scientist and I want to use the supercomputers, how do you get access? I'm asking because in the UK, we have a system based on consortia. So we have big consortia, for example, on turbulence. Then we get an allocation, then we dispatch among ourselves. And I was wondering, how do you get access as a German scientist to your supercomputers?
So our systems are mainly accessible in a so-called excellence-driven access mode. That means that you have to prove the excellence of a project, and this is being, say, reviewed by peers. So that's why it's sometimes also called a peer review mechanism. And then based on, say, this the reports of these reviewers, an allocation committee, which is, say, not a committee which is, say, controlled by us, but it's really, say, scientists which form this committee, make then a decision about who gets access to these resources. I mean, these are expensive resources, and the purpose is to to have mechanisms in place which allows to have, say, the best scientists making use of these resources. And it was really in this mindset why the Jülich Supercomputing Centre was actually, say, the first center in Europe which was making resources available to PRAISE, and through PRAISE making it available to European scientists at large. Because it is whether you have smart scientists doesn't depend on whether you are in a country which can afford of having a big computer. It could also be, we have seen, say, a lot of very good science teams in smaller European countries, which came up with very brilliant ideas. And that's why it is so important to have something like PRAISE in place, because it gives them an opportunity to, say, realize these projects, even if at the end of the day, in the current model, these kind of computers are funded by, say, the German taxpayers. Now, we will see this to change in Europe a bit through a new organization, which is called Euro HPC, where it's now, say, the European Commission, which is also putting itself a lot of money on the table to realize, say, in the first round, 3 pre-exascale systems, plus then 5 petascale systems. But
Great.
for all of them, I mean, the prime access mechanism as it is foreseen right now is through an excellence-driven mechanism. So the question is, do you come up with a proposal which is scientifically sound and excellent, then you have a good chance of getting access to the resources.
Okay, great. Just one final question on this topic is, are you oversubscribed? Are you largely oversubscribed, or are you able to, I mean, if the research project are satisfying all your criteria, will you say that you are very likely going to get funded? You are not struggling to meet the demand, or is it quite challenging?
We typically are, say, oversubscribed. That means that in the call for proposals, and we have different, say, mechanisms through which allocations can happen. I mean, there are the national mechanisms, but there are also, say, the European mechanisms like PRAISE, and they typically receive much more requests than they can actually serve. And that is, of course, a healthy situation, so that you have, at the end, say, the opportunity to choose those projects which, say, are likely to produce, say, the biggest impact in terms of science.
Great, thank you very much. It's very interesting. So you recently contributed to a conference proceeding called, and I'm going to read my note, HPC Systems in the New Decade, What to Expect, When and Where. So I guess I'm going to ask you, what are we going to expect when and where in terms of HPC systems? What's your take on that?
Well, it's of course not so easy to look into a crystal ball, and say a lot of that is driven also by, say, the agendas of different countries or different continents, by, say, the respective funding agencies like the DOE in the US, or then in Europe, there's now this new player called Euro HPC. The main point which I tried to make also as a message to the computational scientists is that we have to, as computational scientists, we have to be aware that there is an upcoming larger diversity of hardware architectures, and that we have to pay great attention in the way of how we write our codes, so that they are, on the one hand, say, sustainable in a sense that we can go from also to a next generation of architectures, but that we even also have the possibilities also to switch between different architectures. And this is a development which we can already see just looking, say, at what is happening, say, for instance, in 2020. I mean, until 2020 in Europe, we essentially had only, say, one big GPU accelerated system in Europe, and that was Pitt-Stained at CSCS, and which really, say, pioneered it. And I think it was very important that they made this step in order to encourage, say, the community to port their applications to GPUs. But now last year, we have seen that more systems accelerated with GPUs have been deployed in different countries, including now the new Dual Booster system at the Jülich Supercomputing Centre. The other development which we have seen in the last year is that in Japan, the Fugaku system went online, which is the last system which is not based on Intel Xeon. And one of the worries which I have a bit is that we have now, say, a generation of, say, computational scientists which grew up with, say, only knowing Intel Xeon, and they have put, say, a very interesting architecture, very efficient architecture in place, which is based on ARM and its new instruction set architecture called SVE. So it's now very important for application developers now to be able to, say, leverage these different kinds of architectures. And this will become even more diverse, because if we look into, say, the roadmap for the current year, 2021 in the US, where, say, it's planned to prepare for 3 exascale systems, where Two of them are based on AMD processors plus AMD GPUs. So basically a GPU architecture which in the last couple of years has not been used heavily for high performance computing, and which comes with its own programming models. Plus then another newcomer, and that is Intel, which is putting, say, yet another GPU architecture in place, which is also completely unknown, say, so far to most of the computational scientists. And it will be, say, a great challenge of how do we actually deal with all these different kind of architectures? How do we make sure that our applications are performance portable? And this kind of heterogeneity, I mean, you can say extend it into other areas. I mean, it also concerns, for instance, the questions about memory architectures. I mean, if we want memory to become faster, then we have to move to technologies which are, say, used, for instance, for GPUs, which are very expensive. They are fast, but they are expensive. And so as a consequence, it's not only the cost, it's also some technical reasons. You cannot afford to have as many of this memory. So you have to think about how can I, say, trade performance with respect to capacity, or maybe have to work with architectures where you have two types of memories integrated. And the same also holds for instance, for storage architectures. It is very difficult to have, say, just one storage architecture which provides you at the same time a lot of capacity as well as a lot of bandwidth. So also there would be a lot of benefit if we could design our applications, our workflows such that we can efficiently use, say, faster storage tiers, which are fast but small, and at the same time have then in the background, say, much larger storage tiers, which are then, for instance, used as archive, where we can then accumulate scientific data because they provide the necessary capacity.
And that's very interesting. I was wondering, what's your opinion, and what's the best strategy to, you say it's going to be very important to leverage all this new hardware that we are not familiar with. And so if you were an application developer in 2020, 2021, what will you do to make sure that your application is, well, or will be ready for those new systems?
Unfortunately, there is not something like, say, the holy grail in terms of programming models. I mean, even so, there has been a lot of research, and there's a lot of ongoing research with respect to different programming models which can hide some of the complexity. At the end, my experience is that it depends very much on also the field and the specific applications, what are the right trade-off. But I think what we eventually have to aim for is to aim for having, say, designs which allow for a separation between, say, a front end, which is more science domain specific, and which is the part which ideally is the only part which is touched by most of the main scientists, and a back end which is then optimized for performance and might be largely designed not by the domain scientists, but actually by software engineers and computer scientists, which have a good understanding of the computer architectures and which are either designed such that they can be used by on different architectures, for instance, leveraging domain-specific language approaches, or in many cases, like for instance, lattice QCD, you might also afford of having, say, different architecture-specific backends. And here it will also be important in the way of how communities organize themselves. I think it will become more and more important that communities collaborate so that these kind of backends could become, say, community code, which is maintained by communities where different people in the communities contribute, so that it becomes more affordable for, say, different scientists to have then backends for completely different architectures. And I think that is, say, the only way of how we can then deal with this upcoming heterogeneity in the HPC architectures.
Great. Thank you very much. And would you say that in Germany, at least, I mean, you see a lot of proposals, and will you say that the community in Germany is ready for these new systems? I mean, you mentioned that you now have 1,000 GPUs available. Are scientists in Germany able to use those 1,000 GPUs, or people are still working on software development and are still trying to get ready and find the best strategies for their solver?
I should correct, it's 1,000 nodes.
1,
each of these nodes
is
a very fat node, and each node comprises 4 GPUs, so we're talking about 4,000 GPUs.
4,000. Okay, sorry.
And that gives you, say, one of the example of say, also how things are changing, right? I mean, you now start to have, say, a lot of parallelism within a single node. So parallelizing over a larger number of nodes is not, say, the prime concern. Mm-hmm. The first concern is, how do I get my, say, application to leverage all the power which I have in a single node before actually to expand beyond, say, multiple nodes. But coming back to your question about to what extent the communities are prepared, this is certainly, say, still a very mixed picture. I mean, we had made, when we, say, started to work on the Joules booster, we also put an early access program in place. And we were quite pleased with the outcome in the sense that we did, say, reach out to 14 teams, and all of them, or almost all of them, really made it then to be able to run on this booster, in part with really impressive success. So we have had, for instance, one team with code which was not GPU enabled at the beginning of 2020, but then in September 2020, when the booster was available, they could run with 25x speed up compared to just only using the available CPUs on the nodes. Mm-hmm. And that was possible in this case thanks to that they had even so it is quite it's an older code. The code was developed in the 1990s. But they adopted at a very early point of time a domain-specific language approach, and that allowed them to migrate in a relatively painless manner than on having, say, a CUDA implementation in this particular case. But overall, I think there is still a lot of work which has to be done by a lot of the computational scientists. I mean, while we have seen a number of good examples where people did have code which was reasonably straightforward, even to accelerate on GPUs. We still have, say, a lot of applications where people are not even able, I mean, to leverage vector units in a single processors, and that means they are not able to fully leverage, say, the parallelism which is in the code. And to add these extra dimensions of parallelism into codes can sometimes be very, very difficult. And I think it's important to really have, say, strong pressure on, say, the computational scientists, at least those which are in need in using, say, HPC, high-end HPC systems, that they are aware that they really have to work on the codes to enable them for being able to leverage these kind of systems. So I think there are quite a number of positive examples, sufficient positive examples that we were very confident that when putting, say, the Joules booster online, that it can be immediately used for doing great science, and that is not empty and waiting for people to develop their code. But I mean, the development is going on, and now soon, say, much larger systems are getting online. And so the number of applications which are, say, already today ready to use these kind of systems is becoming smaller and smaller. So compared to, say, how these systems are growing. So I think it is really important to make this investments into these codes. That is, say, of course, not only a message to the application developers, that is in particular also a message to the funding agencies that it's really important not only to invest into the bare metal of these HPC systems, but to also invest into the application development.
Great, thank you. And So we have a rough idea of the first generation of exascale systems. I mean, you mentioned AMD GPUs and Intel GPUs, but do you have, I always ask this question, it's a tricky one, but do you know where HPC is heading in the future? I mean, do you think there will be still a big push for accelerator technologies, or do you think like the Fugaku system will reshuffle things, or where do you think we are heading?
Well, I mean, even so, the Fugaku is, say, a system which seems to be a more standard processor. It's still, say, a very specialized processor, and that's why it is possible to also, this being, say, quite a power-efficient system. But the Japanese community made a very conscious compromise when it was about performance. It was not their prime goal in reaching, say, more than an exaflop Lampack performance in order to get, say, in the forefront of the top 500. I mean, they managed to do it, but this is now a system which is going to be to stay there for quite some time. But they rather made a conscious decision. We want to have a system which is suitable for a broad range of applications. It was in a very close connection to also a science program. They had a very clear understanding about what are the science areas we want to support. They had also, say, the perspective of getting, say, good allocations on the resulting system. So there was a very strong incentive for then the research teams to actually prepare for this system. But I would not make the mistake in assuming that it's, say, very simple to say, leverage the performance of this system. I mean, you have to optimize for this processor architecture. And now when it comes to the question about what will be, say, the kind of architecture which we will see in the future? Is it just, say, kind of a hiccup and intermediate stepping stone that we have to use, say, the dirty GPUs? I would warn off say, making this assumption. I mean, there is, if we think about these more general purpose processors like Intel Xeon or AMD EPYC, there is quite a significant price to pay when you have all these logics in the hardware. And if you want at the same time keep the power envelope reasonable, then you have to simplify these architectures. And the Fugaku processor, so the A64FX from Fujitsu, is in a large extent a very simplified processor. And if you like, in an abstract manner, the GPUs are also, say, simplified architectures. I mean, they're still von Neumann architectures, but in the way of how they deal with instructions, they are, of course, very much, say, simplified with respect to what we see, for instance, in an Intel Xeon or an AMD EPYC. And I think it is important that applications prepare for that. I think these accelerators are there to stay. And it's not only for technical reasons, there's another reason for that. I mean, we should never forget that HPC, if you look at it from a business perspective, is a niche market. And so we have to leverage the technologies which find a much broader market. Mm-hmm. And in this sense, Fugaku might be a bit of an exception because Fugaku was enabled with a significant public investment by the Japanese government. In other, say, countries or continents, there's also, say, the decision of not doing, say, similar kind of investments, but really, say, pushing for use of, say, commodity technology. And HPC is, to a large extent, not driving anymore this kind of commodity technology. That was to some extent the case in the past. And so for the accelerators, which we see now emerging in the HPC systems, I mean, they have a much wider market, in particular, say, the machine learning market beyond HPC. And this is the market which eventually provides, say, the revenues for the companies for developing then the next generation. And that is also, say, from what I believe is the more important argument for the assumption that we will see also in the future, say, these kind of heterogeneous architectures which are leveraged in, say, power efficient compute accelerators.
Thank you very much. I have one final small question. Where and when are we going to have an exascale computer in Germany? And is there any plan at Jülich to have one, or it's still a bit too early to talk about it?
Well, I would say at this point, the Jülich Supercomputing Centre has a very clear ambition, and that is namely the ambition of hosting one of the two planned exascale systems funded by EuroHPC. Of course, it is at the end EuroHPC to decide on which hosting entity they give most of the credits for actually hosting such a system. And with that, I mean, our timeline is largely then depending on EuroHPC. At this point, they have the ambition on realizing an exascale system in 2023. We have to see whether this will work out, but this is at least where also a timeline where we are preparing for, and we are planned to be ready for being able to host an exascale system in 2023, which would then be an European system. And I expect that the other German supercomputing centers will try to follow also thereafter, but these are definitely very expensive systems. So, I mean, the technologies are now becoming ready such that within a reasonable power envelope, one could realize, say, an exascale system. But of course, there's still, say, large challenges to get, say, the funding ready for actually being able to procure such systems.
Thank you very much, Dirk, for all your input and for discussing with us. It was really nice to talk to you, and we wish you all the best for all your future endeavors. That's it for today. If you want to learn more about the ExCALIBUR initiative and the UK Turbulence Consortium, please have a look at the website, and I will also advertise this podcast on the Twitter account UK Turbulence. Thank you very much, Dirk. Again, and thank you everyone, and hope to see you soon in a new episode. Bye-bye.